Today I will speak about the run-up problem for the linearized shallow water equations. This is a joint work with Sergei Dobrokhotov, and based on the results mainly obtained by us together, with the occasional participation of some other people from our research group. And so I will start. This is what I will speak about today, statement of the problem, homogenization away from the boundary and near the boundary. Well, okay, and so let's proceed to mathematical model statement of the problem. Well, if we are to describe some gravity waves on fluids, say tsunami waves, then in the linearized shallow water equations approximation, the equations can be reduced to the wave equation written here for the free surface elevation. Here, this is wave equation written in the divergence form, and c square of x is just equal to the square root to g times d of x, where d of x is the basin depth variable function. Well, and g is the acceleration due to gravity. And for simplicity, in the following, I will assume that g equals to 1 in our system of units, so not to write it at all. In this problem, if we speak of propagation of tsunami wave, there is a natural small parameter, which is the ratio of wavelength to the basin size. Here we have the basin, some perhaps lake with an island, and here is the initial perturbation. Its size is small compared to the overall size of the basin, so we have a natural small parameter h, and so it is natural to use semi-classical approximation to obtain asymptotic solution of this equation, namely the technique based on Maslow's canonical operator. This is, of course, well-known, well-developed technique, but you know there are two difficulties here. Well, okay. So the first difficulty is that on the boundary of the domain which represents the coast, the depth is 0, and the propagation velocity is also 0, and so the equation degenerates on the boundary. This is the first difficulty. Well, and the way to tackle this difficulty is the uniformization procedure, of which I will speak a few words later. Well, but there is also a second difficulty. The depth d of x, if we speak of real ocean, has not only smooth variation, but also rapid oscillations. Here we have two pictures showing parts of ocean bottom. I don't remember where exactly, but never mind. Well, and so the problem is that the size of these oscillations, the horizontal size of these oscillations, is much less than the typical wavelength in the tsunami propagation problem. And so if the coefficients of the equation have rapid variation, then it is not very good to apply semi-classical methods. So first of all, we must somehow deal with this problem. And the talk is just discussing this second problem, the problem of rapid variation of the depth. And of course, the first idea which comes to mind here is the use homogenization methods. Well, homogenization theory, this is just the theory that studies equations with rapid variations of coefficients by reducing them to equations with slow varying coefficients. And this is a very well-developed theory. Here is a very incomplete but still long list of people who studied homogenization. If I were to present the complete list, this would take up all the time of my talk. I don't wish to do that. So, and in the simplest case, the homogenization is as follows. If rapidly oscillating coefficients are represented in a function of this form, where mu is a small parameter describing the rate of variation of coefficients, and homogenization amounts to averaging the coefficients over the period. This f is periodic in the fast variable y, and so we just average the coefficients, And this is approach suitable for periodic media. And of course, there is well-developed theory which proves that under this homogenization procedure, we obtain equation which, in certain sense, approximates the original equation with rapidly varying coefficients. However, in our case, in our problem, this approach doesn't work at all. First of all, the ocean bottom is not periodic, so we at least need to assume that this depth depends not only on the fast variables but also on the slow variable, where f of xy is 2 pi periodic in the fast variables, but somehow it depends on x also. And in this case, this semi-classical approximation was developed in the paper by Brüning, Gruzhin, and Dobrokhotov based on some early results mentioned here. However, this hypothesis is not good either, for two reasons. First of all, the bottom irregularity makes it hard to believe that our depth function is periodic in the fast variable. There is no reason for it to be periodic. And second, even perhaps more important, is that assume it were periodic, but we know the bottom function, the real problem, from measurements, for bathymetry measurements. And so this is equivalent to saying that we know this function d of x mu only for one specific value of mu, not for all values of mu. This is given by the measurements. And so, knowing this function, we cannot reconstruct the original function of f of xy, even if it were somewhere here. And to obtain computation formulas, we need to know this function. So this model is also not very suitable for our problem. And we have a task of developing a homogenization method which doesn't rely on the representability of coefficients in some form like this, and only uses the for computation, uses only the results of real measurements of this bathymetry of this bottom function. And so this method should provide efficient computational formulas that can be applied to actual data. And so, well, let us discuss how we do this. And first, we separate the difficulties and we deal with the problem away from the boundary. So we assume our equation is non-degenerate. Say our ocean is infinite and occupies the entire plane. Well, okay. So the main assumption that we made is that the depth function is represented as shown here in the framed formula. This is a perturbation of a function which varies slowly by some rapidly varying function. So the first term d naught is varying slowly, all derivatives are uniformly bounded, and the second term d1 is rapidly oscillating, which means that each time we differentiate with respect to x, we get a factor mu to the power of -1. So, but here we have also another parameter, delta, which has the means of ratio of vertical size of bottom oscillation to the average basin depth. And this is, all in all, three parameters which we have in our problem. First is this semi-classical parameter h, the ratio of wavelength to the basin size. Second, this is parameter mu, which is the ratio of horizontal size of bottom oscillations to the basin size. And third, this parameter delta, which describes the bottom as a perturbation of a smooth function. And we will have some further assumptions which we add along the way. Well, okay, so the first problem which we must solve is to describe the averaging procedure. In the case where our function was 2 pi periodic in the fast variables, averaging was simple. We just integrate over the variable y. Here this is impossible, but we have a very convenient substitute. So let us consider this convolution written here. We take some function phi, from the Schwarz space and write this integral where mu is taken to the power of gamma, and gamma is an arbitrary number in 0, 1. And we say that our function f is locally averageable if this integral is a non-oscillating function, regardless of which phi and which gamma we take. Well, and if a function f is non-oscillating, then we can define the local average as follows. We just take this convolution, but not with an arbitrary function phi, but with a function phi specifying some special properties. And these are the following properties. First, the integral of phi is equal to 1, and if we multiply phi by an arbitrary power x to the power of alpha, then we obtain 0. So this is known as a Sobolev averaging kernel, of course. Well, so for this local average, we have the following assertions. First of all, it is well defined. Regardless of which function phi we take and which gamma, we obtain the same result, modulo O to the power of mu to the power infinity. So in the all terms of perturbation theory, we obtain the same result. And for lack of time, I sometimes show that I miss saying about this O of mu to the power infinity, just is with the equality. Second, if our f comes from a function 2 pi periodic in the fast variables, then this local average coincides with the usual variable obtained by integrating over the fast variables. Third property, that this local average changes nothing for non-oscillating functions, and it commutes with differential operators with non-oscillating coefficients. So this is our averaging procedure. And with this procedure at hand, we can proceed to homogenization. Well, so let us write the main equation of the homogenization procedure. Here is our operator h hat, which is the spatial part of the wave operator, which we study. And for convenience, we have multiplied it by mu square, so that in what follows, we only deal with mu differential operators. All derivatives are multiplied by appropriate powers of mu. And so our main equation for homogenization is this. H chi is equals to chi L plus R. Here, chi and L are unknown mu differential operators which you need to find, and R is the remainder small in some sense. Well, and here chi may have mu oscillating coefficients, rapid oscillating coefficients, and L needs to have non-oscillating coefficients. So this is the meaning of this. This procedure, in fact, resembles reducing something to normal form, where H is the general operator and L is the normal form. When we reduce something to normal form, we kill undesirable terms. What is undesirable here? We try to kill rapid oscillations. So from oscillating operator, we obtain non-oscillating one. And if we succeed in solving this equation, then we can replace the operator H by L hat, solve the equation with this operator, and then apply this chi and obtain solution of the original equation. That's a very simple idea. And let's proceed to how we do that. Well, so here are two unknown operators chi and L, and we seek them as mu differential operators with symbols of this form. If we substitute them into our equation, then we obtain this equation. I do not write the remainder here. Well, this is everything except for the remainder. And if we take this equation, multiply out, match the coefficients of like power of delta, then we naturally obtain a chain of recursion of equations, the first three of which I have written here. And here the diamond stands for the twisted product of symbols, that is for the product corresponding to the product of operators. So, say, H0 diamond chi1 is the symbol of the product of operators H0 and chi1. Okay, so the first equation is very simple to solve. We obtain L0 is equal to H0, as would be expected because it is perturbation theory. And, well, so we see that the left-hand side of this equation is some operator applied to the symbol chi1. And it turns out that this left-hand side can be written as follows. P hat, well, this must be not F, but chi k, sorry, plus, so this operator P applied to chi k, plus remainder. The remainder can be taken into account using perturbation theory. So the main thing is to solve equation with this operator P hat. Well, I should note that if we had usual differential, pseudo-differential operators, then the symbol of the commutator would be the Poisson bracket of the symbols. Here, this is not the case, because one of the symbols is oscillating. And so we obtained a totally different result written here. Well, so let us consider, say, the first equation. It reads now P hat chi1 is equal to L1 minus H1. I dropped the remainder, of course. Let's apply averaging on both sides of this equation. So we, because averaging commutes with P, we obtain that this averaging is O of mu squared. So in the first term, we just get that L1 is equal to the averaging of H1, averaging X coefficient-wise. So we find this. And so we must solve this equation for chi1, and we can solve this entire system if we have two conditions. First, the condition that the average of the right-hand side is 0 is not only necessary, but also sufficient for the solvability of this equation, P hat U is V. And second, we see that here in this system, we need to multiply rapid oscillation functions. And so for the procedure to work, we need the product of averageable functions be averageable again. This is of course not the case in general, and so we must somehow restrict the class of our symbols. Let's deal with this. So we introduce this definition. Regular algebra is an algebra of locally averageable functions with respect to Poisson multiplication that contains all non-oscillating functions and is invariant under mu differentiations. So in this algebra, we have always the product of two symbols in this algebra also belongs to this algebra. So the product of averageable functions is averageable, and we can differentiate without leaving the algebra. And so let's give two examples. A trivial example, which is functions which are obtained as from functions of x and y, 2π periodic and this fast variable. And the second example is the algebra of almost periodic functions in the fast variable, where the frequency set satisfies some Diophantine condition. I would not elaborate for lack of time, but this is also a very important example. And for the case of functions coefficients independent of the slow variable, this was in fact considered by Sergei Kozlov as early as 1978. Okay, so these are two examples. And now we can proceed to the solvability of the homological equation. And we see that if A is one of these regular algebras, then everything is okay. The equality of the average of the right-hand side is necessary sufficient conditions for the solvability of the homological equation. And so this does the trick for the case of basin without boundaries, if we take this, the knot is greater than some constant, so the depth is greater than the constant, then this operator pi is uniformly elliptic and the chain of homological equations is solvable. And we can, in fact, write more or less explicit formulas. And for the generalized shallow water equations, we have this, if we have this relation between the three small parameters, then along with the original problem, we consider the homogenized problem where D is replaced by its average. And then the theorem states that the difference, in fact, in the energy norm between the solution of the original equation and the average equation is small. Okay, so let's proceed to what we do with so I omit to prolong time. Well, what we did with the boundary degeneration. If the equation degenerates on the boundary, then we have the main difficulty, which is as follows. When we try to construct semi-classical asymptotics to such an equation, the trajectories of the Hamiltonian system reach the boundary in finite time, simultaneously going to infinity in the momentum variables. And so the solution to this problem is uniformization procedure, which we developed. This is, we lift this equation to a less degenerate equation in a higher dimensional space, and for this equation there is no problem constructing asymptotics. And this is possible if we have the Shilov-Beach assumption that d of x, which is positive, strictly positive in the domain, it is zero on the boundary, but the gradient of d of x is not zero everywhere on the boundary. So then this procedure is possible, and so it is an example of it. Model example, if we consider half plane, x1 greater or equal to 0 in R2, and consider this equation, which degenerates on the boundary in this way. Well, let's consider function n of y and t given by this formula. Then it is a rotation invariant solution of this equation. So this equation is much less degenerate in some sense than the original equation, because first, the spatial part of the wave equation is Hermander hypoelliptic, which provides appropriate estimates for the solution. And second, the trajectories of the corresponding Hamiltonian, which is written here, outside the zero level state of Hamiltonian, are extendable infinitely. Well, and so we can solve this, the Cauchy problem. And, well, so to apply homogenization, we make this assumption, d of x is again the perturbation, but now d naught is satisfying the shallow beach assumption, and d1 is the product of d naught by a mu oscillation function. Then we can solve the main equation, this equation, but here r is no longer small, but it's only small outside a neighborhood of the set where h naught is 0. And if we construct a semi-classical asymptotic solution whose Lagrangian manifold does not meet this set, then r applied to this solution gives approximately 0, and so we obtain the solution of the original equation by the same method, by applying chi. Well, okay. So here are some papers concerning this, and thank you very much for your attention.
Thank you for very nice presentation.